All right. All right. Good afternoon, everybody. Thanks for coming to my talk. Honey, I stole your C2 server. So my name's Andy Rector. I'm a consultant with Mandiant, based out of the San Francisco office. I've been with Mandiant for over 2 years. My primary focus is digital forensics and incident response. During that time, I've conducted several enterprise investigations for Fortune 500 companies involving all sorts of different industries, high tech, healthcare, financial, you name it, all over the place. So what I'm going to talk to you guys today about is an investigation that Mandiant did in 2016, late 2016. So I'm going to give you a high-level overview of how that investigation went, what kinds of stuff we found, and just overall what that investigation looked like. And then I'm going to go into the analysis of a C2 server. So we were able to obtain a C2 server. It's going to tell you about how that whole process worked and how rare and kind of exciting the analysis was, and some interesting findings that came from a Postgres database on the C2 server. And then lastly, I'm going to talk about PostGrok, a Python program that I made to carve Postgres rows from a flat binary file. Okay, so before we get into what made this investigation so rare and exciting, you should understand what a typical investigation looks like. So what normally happens is a client calls us. They've identified some malicious activity in their environment, either by themselves or through some external notification like law enforcement or something else. So we have a scoping call. We decide to deploy technology. So we deploy some network-based technology and some endpoint-based technology. This gives us full coverage of their environment, or as close to full coverage as we can possibly get. And then we begin the investigation itself. So this is where we, our tagline, find evil, solve crime. This is kind of a cyclic cycle where basically we search the environment for indicators of malicious activity. Once we find something, we perform analysis on the system or whatever the source of evidence is. Once we find activity there, we continue searching the environment and identify additional evidence of activity. We keep pulling those strings until there's nothing left to find. Once we're able to completely scope the environment and get at a comfortable level that we've identified as much of the activity as we can, we perform an eradication event or remediation event where we kick out those pesky attackers and also try to improve the security posture of our client. So this is where we do things like blocking C2, rebuilding systems, and all the other things that go along with that, like enterprise password resets. Once that's done, we perform some post-remediation monitoring just to make sure those pesky attackers don't come back into your environment. That usually lasts anywhere from 2 to 4 weeks, just to make sure that everything's good, everything's at tip-top shape. Once that process is done, that's kind of the end of our involvement with our client, and it passes on to a different business unit and so on. So this investigation actually kind of started out pretty similar to everything else. So this is a Fortune 500 financial-based client, and they were aggregating Windows event logs into a SIM interface, and they identified some suspicious service installations. And this was in September of 2016. So what did that look like? Something like this big, huge, ugly blob. Just a show of hands, has anybody ever seen something like this? Yeah? A couple people? If anybody knows maybe what made this or what this is an artifact based off of, just yell it. Anybody? So yeah, Powersploit Empire, very related. So this is actually an artifact of Metasploit. So for those of you guys that don't know what Metasploit is just a freely available exploitation framework. It's used by pen testers, but we also see it used by a number of different threat actors, including financial-based threat actors and even some APT threat actors. So some of the things that kind of stand out about this. So it's a service installation, and the service installation is a 16-character, really random name. Now, maybe you name your services super long 16-character random names, but I don't, and I don't think most programmers all name their services that either. Some of the other things like comspec, which is just an environment variable for cmd.exe, PowerShell being executed, and then a base64 string. Honestly, whenever you see PowerShell being executed with a base64 encoded string, it's always something kind of interesting and something that should be looked at. So basically what this results in is a memory resident backdoor. So if anybody's familiar with Meterpreter, this is what this looks like. This will result in Meterpreter session. So we understand that this came from Metasploit. So we can use what we know about Metasploit and the artifacts that it creates to do some intelligence-led scoping. It allows us to scope this environment very quickly. So some of the things that we look at are these really random workstation names. So Metasploit actually implements their own version of SMB, the protocol to connect to other systems in an environment. And so when they do that, they just pull random workstation names. And these workstations, they just throw that field in without actually just pulling the legitimate workstation name. So what we can do as investigators is search security event logs for these network logons involving 16-character workstation names. So that's one way we can track lateral movement in an environment. We also search for service installations. So these 7045 event log messages that contain comspec, base64 encoding, PowerShell, very much the type of stuff that you just saw in the previous slide. So 72 long hours. Anybody want to take a guess as to which 72 hours that was? If you're thinking the weekend, you probably work in incident response because that's exactly what it was. So it's the weekend, we have to work it, and we are able to quickly scope this environment. So we identify 129 systems that were compromised by the attacker with evidence such as the stuff that we just talked about, the service installations, lateral movement activity, 116 compromised accounts, just kind of cycling through the different credentials, seeing what works. And also the initial attack vector was able to be identified. This turned out to be a very simple, poorly configured public web server in an area of the client's environment that they just weren't paying attention to. So this was a SQL injection that could have been easily avoided, but they just weren't really aware of the system and how it was configured. So now that we have that side of the investigation done, we can talk about the C2 server. So in my mind, when we do investigations, we have a two-sided perspective. So the perspective from the incident response investigation or the defenders, the enterprise defenders, we have that perspective. And that perspective is really framed by the artifacts and the technology we have available. So we can never be 100% sure that we've identified every single system for a number of different reasons, whether it's our technology isn't deployed everywhere, or not every system has the artifact that contains that gold piece of information that's going to solve the investigation. So we can do the best we can with the artifacts and technology we have available. Now, if you've ever thought, boy, this investigation would be a lot easier if we had a C2 server, well, I think that all the time. It'd be really nice. But it's not very easy to get a C2 server, right? They're not in our possession. So is there a way to do that? Maybe if you're not in America. But the attacker's perspective is something that would be really nice to have and highly sought after. So let's go back to that service installation. So this service installation can actually be used to extract the C2 server, the C2 server IP address. So how this works is you identify the base64 encoded data and the compression scheme. So this information, we have the base64 encoded scheme and then the compression. So in this case, it's gzip. In some other cases, it could be a different compression scheme depending on whatever the platform is being used. Cobalt Strike uses a slightly different implementation of this, but it basically results in the same sort of memory resident backdoor. So once you do that, you get a second, basically an encoded layer 2 script, right? And this script has a number of different functions. It's got some more base64 encoded data. So when you see more base64 encoded data, why not just keep decoding? So we decode this second layer function, and this results in shellcode. And I won't pretend to be a shellcode expert, but the way this works is basically we disassemble the shellcode, identify the appropriate network calls, and once you identify that, you can basically reverse, these are going to be stored in Little Endian format, so you reverse the byte order, and you're able to convert that to ASCII, and then you'll have the IP address that is configured for this, this backdoor. So at this point, we've identified the IP address that the attacker is communicating with. We know the IP address of their C2 server. So as part of a very routine status update, we provide this decoded IP address to our client. Now, this is a pretty normal thing. We always like to be very transparent with our clients and give them as much information as we're finding it, as we understand it. We provide that information to them so they can do whatever they want, whether it's make a business source decision on whether they want to block right away and risk playing like a whack-a-mole type game, or whether or not they just want to use it so they can do their own monitoring as well. So we provided the IP address, and what we discovered is that the client actually recognized the owner of the IP. This is going to be a bit of a wild ride here. So the client actually just did a simple whois on this IP address, identified that this was a small-time competitor. So they actually had a relationship with the owner of this IP address, and they had actually just ended it the week before this attack began. So let's all put our tinfoil hats on and see where this goes. So they had just basically described this as a small-time competitor. They recognized this IP address. So what would you do? Well, how about you just ask? Just ask this third party for their C2 server. So the client called them up and said, hey, you have a server that is interacting in a malicious way with our environment. We're going to need to just take that. Please give us that server. I'm not sure they said please, to be honest. They did. They just gave it to him. They gave him the entire server, which is really, really strange and weird. And if any of you guys interact with lawyers, lawyers probably get really squeamy about this. I know our lawyers did. Like, is there any legal ramifications to doing something like this? Well, if you just freely give things away, it turns out, no, not really. So during the next status update, the client basically contacted us and said, hey, remember that C2 address you gave us? Well, we have the server now. So I'm not going to drop this mic, but that would be how their conversation went, which was pretty interesting. So we're like, okay, okay, what do we do here? So they said, well, how would you like to just image it and do analysis on it? So of course, we're all going to be fighting to do that. So yes, we did. We went over and imaged the system, which is pretty awesome. And these are real pictures, by the way, of the C2 server that our analysts actually took while imaging it, because we were going to document the hell out of this. So this is real pictures. They just booted. They just this is an entire rack mountable server that was provided by this third party to our client. So what we did is just basically plug in a keyboard, some mouse, a monitor, and conduct a live forensic image of the server. Cool. So now we have a C2 server. We have an image of it. Let's put this into our forensic lab and start performing analysis, because this is really crazy weird, and we don't get to do this very often. So what did the forensic analysis of this look like? Well, this server was a Windows server, 2008. What we identified is that the attacker had created their own account on the system. They had done some privilege escalation and credential harvesting techniques. So basically, they executed Mimikatz and got creds. Awesome. It gets even better. these are some ballsy attackers. So what they did is they downloaded VMware Workstation on the server, which is a pretty big program. And then they downloaded a Kali Linux ISO, which is also pretty big, by the way. So nobody's looking at that network, apparently. They then installed a Kali VM in July of 2016. This is, keep in mind, 2 months before the attack on our client began. So this is obviously where the really interesting things are going to be. We need to go deeper. This is a little bit of an investigation in inception. And we're also switching gears. We're going from Windows forensic analysis to Linux forensic analysis. So this is going to be the interesting stuff. So we export that VM and begin the analysis again. So switching gears, Linux forensics, let's look at some of the interesting artifacts that we have available to us. So we have some valuable secure logs that basically showed that the attacker was connecting from a low reputation IP address, something from DigitalOcean. We also identified that it was being scanned like crazy because it's a public-facing Kali server. So that was kind of fun. We also identified an interpreter configuration file, basically just the configuration file for their TCP listener for when the backdoor made a connection back to the C2 server. We identified some access to some of the tools that are already installed on Kali by default. So the SQL map, which, like we said before, they had used a SQL injection technique to gain access to the environment in the first place. So SQL map might have helped identify that. We always perform keyword searches when we have a forensic image. So some of these were really revealing. First, we ran searches for some of the accounts that we saw the attacker use, some of the IP address, some of the systems, and basically it allowed us to verify that yes, this was certainly the system that they were using. We're seeing our client's data on this system. This is pretty bad news. So some of the stuff that was really exciting actually was located in not only in allocated space, but also in Postgres, basically in Postgres files. So these Postgres hits kind of led me to look at the Postgres history. So this tells us a bit of a story. So Postgres history basically showed us that they had created a database, several iterations of database actually. They had connected using a couple usernames and passwords. The thing is that Postgres is pretty messy. It's not something that you can just export a file and load it up into Postgres.exe and everything's perfect. Just read it like a SQLite database. It's actually a collection of files. And they're all just flat binary files. There's depending on the size of the database, there could be hundreds of them. So and each one of these files kind of represents a table in the Postgres database itself. So it wasn't very easy to look at. It wasn't a publicly available parser. But knowing that, one of the things that you can do with Metasploit is back up your information or save all your information to a Postgres DB. And something that you can do, and that's actually kind of encouraged by Metasploit or the Metasploit developers as well. Because attackers are people too. They're probably not going to remember every single credential they stole. They need to have a way to track all this information. So, since there wasn't an easy way to just kind of export the database, why not just boot up the VM itself? So I just said, well, I have VMware Workstation 2, worked well for the attacker, I can do that. So it turns out that as I booted this thing up, it was password protected. Also, not a big deal with Kali Workstation. So boot this thing up into single user mode, and then basically configure the grub interface to execute a bash shell. So as soon as it booted up, it loaded a bash shell, and I can change the password. So I just changed the user's password, and now I had access to the attacker system. So I felt really cool at this point, because I don't know about you guys who do incident response. I spend way too much time in Microsoft Excel doing filters and tagging things red. So this was really exciting. I felt like I had just like executed got system impersonate attacker on this entire thing. So this was really fun. This is really cool, a nice change of pace on how how incident response typically runs. So Metasploit is used to attack things. I bet you didn't know you could also use it for incident response. So in this case, basically I could leverage the PostgreSQL history to obtain critical database information. So what does that mean? Well, I know that they created a user, MSF. They created a database, also called MSF. Also, these things contain the username and password. So MSF, not a crazy password here. So actually just use the MSF console or Metasploit's console to connect to the database directly. So I can, or not connect to the database directly, but to actually interact with the Postgres database. Lots of really cool things. So what I could do using Metasploit is execute commands like creds, host, loot, notes. Loot being particularly interesting as a kind of a sexy name, but it also shows us the kind of post-exploitation modules the attacker had executed. Notes and services, basically just showing us kind of the reconnaissance that the attacker has done across the environment. Vulns, whether or not they've identified any vulnerabilities in systems, and then whether or not they actually exploited those vulnerabilities, their status on it. This is really cool. This is a lot of really good information. But it wasn't perfect. Not everything had timestamps. And for an incident responder, timestamps are kind of everything. Timestamps frame the information that we are gathering and the artifacts that we found into a perspective that we can basically show the client and they can understand what has happened. Without those timestamps, the value of the artifact is lessened, really. It's good for obtaining indicators, but less valuable for framing where they occurred in the attack. So I wanted more detail. So I figured, okay, well, I use Metasploit to interact with the database. Why not just interact with the database directly? So using PSQL, I just connected to the database directly. This is awesome. So lots and lots of tables, as you can see. Some of the cool things that I really liked is like the Metasploit credential public. So you can see a couple of things, like it's got created timestamps, it's got updated timestamps, it's got the actual usernames. These are the actual tables from the C2 server itself. So I can see the different accounts that the attacker had actually identified and harvest credentials for. So these are just a couple of them. So credential realms. So this is going to be the domains that the attacker has enumerated. Also timestamps everywhere. Sessions is going to be a little bit hard to see, but sessions being the most cool thing you could possibly see in a Postgres database that is for Metasploit. And the reason it's so cool is because these like big old base64 blobs actually decode to session information. So this is going to show us how the attacker actually configured their payloads. So it shows us username, password, the network that they enumerated, what they were scanning, a lot of highly, highly detailed information. The Postgres database stores entire interpreter sessions and the configuration that the attacker used, including every command they executed within Interpreter. So if they uploaded a file, it's there. If they downloaded a file, it's there. If they dropped into a shell and executed commands using a command shell, it's there. And what else is there is output. So they execute netuse, you'll see the output, the shell output stored in this Postgres database. Entire Interpreter sessions. There is nothing left to the imagination as to what the attacker did in our environment or in the client's environment. This is really, really powerful, great information, and really just paints a pretty amazing picture about what's happening here. So at this point, case is solved, right? The timeline right itself, I mean, we have the perspective from the incident response investigation that we can compare with the perspective that we get from the attacker's C2 investigation. It's all there, and it all overlaps, and it just meshes together perfectly. Every blank was filled in from the attacker's, from the C2 investigation itself. So this is awesome. Client loved it. This makes for happy client, happy consultant. Everybody's happy. This is a big win for us, really. So PostGrok. PostGrok is a tool that I developed based on this investigation. So some of the inspiration was identifying additional victims. So like I said, the attacker had access to the system since the C2 server itself since 2016, so July of 2016, 2 months before we even were contacted by our client. In the Postgres history contained evidence of prior deleted databases. So I wondered if there was any way to recover those databases. What kind of information kind of led me to even believe that there was something to recover. So besides the Postgres history itself, this could be verified via keyword searches. So in the same way that we ran keyword searches for our client and client information, those keyword searches, you could also just search for some generic commands that the attacker were executing. So if they were executing net use a lot, I could keyword search for every net use and see in an allocated space that there were hits that contain domains, passwords that weren't identified in the resident Postgres database. So I knew that there was additional information about other victims on the C2 server. They had access to it for at least 3 months, but we only saw evidence of attack for our client. So I wondered if anybody had tried to do this before. There wasn't anything obvious. There was a tool that wasn't publicly available that was capable of recovering different artifacts from different database management systems, but the focus wasn't Postgres. So I needed something that was going to specifically cater to the needs of Postgres and what I had in mind. So I'm not a programming genius. I don't do a whole lot of developing, but when I have a chance, I do like to kind of like dabble in it a little bit. So PostgreSQL is open source, which is really nice, but it's all written in C. I don't have a strong background in C, so I didn't immediately know how to read all of this information. So it was kind of a fun exercise in research about how Postgres worked, but also on the development work cycle and how to even read code from another language. Luckily, these guys have a strong development team behind them, and a lot of their code is documented pretty well. But still, reading C structures was a fun ride, to say the least. So I created a tool called PostGrok to carve all PostgreSQL rows from a flat binary file. So this is something like a raw image. So it doesn't have to be just a raw image. It could be just the specific files located in the Postgres installation directory, or it could be an entire forensic image that's collected. So I'm going to take a little bit of a deep dive into Postgres and what that whole, just what that whole structure really even looks like. So hopefully this doesn't get overly boring. So the anatomy of a Postgres database. So a couple of the terms and definitions to understand. So tables. So these are going to be the actual physical files located in the Postgres installation directory. So each one should be considered a table. Now these tables are going to be made up of pages. And so a table could have 50 to 60 or 1 or 2 tables. It really just depends on the size of the table itself. Within each page is going to be a row pointer, free space, and a row entry that contains the row data itself. So this is kind of a visualization of what this looks like. The red being the table header itself, the blue being the row pointers that are going to tell us where our row data is located, and then the yellow stuff is null space, which we'll talk a little bit about, and then purple being the row data itself. So you can kind of see at the bottom, it's got some information like command. Well, that's a command that was executed through Meterpreter. So the page header itself. So the page header itself is a 24-byte structure. It's got some version info located in it. From this header, what we can gain is information about the number of rows we're going to find in this page, in this Postgres page itself. So this is helpful for understanding how many rows to expect in a page and how many rows we're going to need to parse. This is part of also what my tool does is actually look for these types of headers. It's not an obvious header like MZ header that's going to give you, obviously this is a PE file. So what I had to do with this is kind of look for a header that looks like this, using some certain entropy checks about what can't happen in this sequence of bytes. And so far it's been really successful with identifying the start of a Postgres page. So the row pointers itself, they're 4-byte structures, very important for telling us a couple of things: where the data is located, the offset within the page itself, as well as the size of the row. So the size of the row is going to be the entire row from the row header all the way to the end of it itself, the end of the row data. The free space. So free space is going to be the section that follows those row pointers. And what basically can happen is that as additional data is added to the page, so the row pointers will be added from the top, and then row data will be added from the bottom. So in a Postgres page that has a lot of rows in it, there may not be any free space. So that's something that also had to be accounted for in this tool, PostGrok. So the row entry is split between two things. So you have a 24-byte header that contains information about the row, and then it also has the row data itself. This is the type of data that you would see displayed if you ran something like a select star from table name. That would be the data. This will be where this is being pulled from. So the row header, a couple of things that stick out, is like the row insertion ID and the deletion ID. So when a row is inserted into a Postgres page, it gets assigned an ID for when that occurred, and then a deletion ID if the row is deleted. So when a row is deleted, it doesn't actually mean that it's deleted from the disk. It's just deleted from the Postgres file. It gets an ID, and you can say that, well, I'm not going to display this because it was deleted. But it can still be recovered. So you can also get the number of attributes. So think of attributes as the things that you would see as columns. So these would be the column headers. So each one of those is an attribute of the table itself. The offset to the row data is going to show where the data actually starts. And the reason this is important is because rows that have lots of attributes or column headers, this information will basically track which one of those are in use or not in use. So you have to be able to understand where this data is going to start, so you can track whether or not these columns are going to have data in it or not. So the row data itself is going to be kind of the different data types that you would expect to see. So integers, dates and times, variable length strings. This is where a lot of the meat of the program lives. This was kind of challenging because there's not an obvious way to understand where different attributes begin and end. And so you just have to basically look for certain signifiers that say, well, this is going to be string data, and the string data is going to be this length. And so there's a bit of guesswork, so this is why this is really a carving utility. So PostGrok and its capabilities. So like I said, this is a Python tool that is going to thoroughly understand PostgreSQL. The main capabilities being that it's going to carve rows from a flat binary file. So this could be the files located in the Postgres installation directory, or it can also be a forensic image. You can also do keyword searching with it. So if I know that I'm specifically looking for entries relating to a certain username or I'm looking for entries relating to Metasploit public credentials. I can search for that and just get only that type of data. It can export to CSV or Excel, and officially just supporting version 9.5 of Postgres right now. I suspect it actually supports more than that. I just need to continue to do more testing on this tool. So it is on GitHub. So if you too have a C2 server that an attacker used to back up their entire thing to a Postgres database, run this tool. It'll probably get you a lot of data. So it can be pretty exciting. PostGrok Findings. So some of the cool things that we were able to find with it is that there was full interpreter sessions occurring all 3 months that the attacker had access to the system. So in July, August, September, everything. Over 1,400 compromised credentials, over 48 enumerated domains. It's a lot of activity. And some of the things that this looked like, basically we could do some heuristics on the type of data. So as I said before, this Postgres database is going to store all the modules the attacker executed. So I thought it was kind of interesting to see, well, let's see what their most popular post-exploitation modules were. So probably unsurprisingly, this credentials SSO, looking for single sign-on credentials from a system, as well as AD computers, just enumerating ADs, smart hash dump, credential collector, a number of different post-exploitation modules that they basically were running almost every time they would be on a system. Some of the ones that are less common are application-specific ones, like Tortoise SVN or Outlook. So those systems I would consider investigatively maybe even more interesting, because it seemed like they were searching for something and targeting an application specifically, maybe because it had something interesting on it that they were looking for. So some of the things that we found based on PostGrok and the interpreter sessions that were extracted is that the attacker actually added their user account to victim systems. So we talked about how they did it on the C2 server. Well, this is actually what it looks like, and this is what PostGrok would carve out. Basically, they add their user, Mava2, and that really, really sophisticated password. That's not too bad. So then basically there's the output to it as well. You can see that it was successful. They were successfully able to add their user, a new user to a system. Some of the other things they did, they were uploading web shells a lot. So a lot of victims got web shells. Everybody got a shell, which is pretty fun. So they uploaded something publicly available, this ntdaddy.php, also other shells called command.php. And then you can see they run, they always run like a dir or an ls command to basically see and verify that their uploads worked. So on the server, you can see that they also, that it actually worked. It's on the remote system, and it's called 0.asp or 0.php. Attacker data theft. So some of the things that they were specifically targeting outside of just XLS documents were web.config files, looking for different configuration files for web servers. Like I said, there seemed to be an obvious interest in web servers and uploading web shells to these systems. So some of the things that they downloaded, though, outside of that on users' workstations were things like Wi-Fi pass.xlsx. And we saw this a lot even in our client's environment. The attacker actually just downloading passwords.txt, passwords.xlsx, wherever they were storing passwords. These users were storing passwords on desktops or user directories all over the place. So just kind of like looking for kind of just lazy users storing passwords on their desktop, common attacker things. So we also see that they view FileZilla contents and downloaded another Excel file. Some of the fun tradecraft that we saw, so they used PSExec, which is just a common Microsoft utility you can use for lateral movement. So they started basically a netcat shell to their command and control server using PSExec. And then we also see that they have other files. So one of these files that are pretty interesting, file.zip. We also see nc.exe, psexec.exe, basically a staging directory for this attacker. So keep in mind file.zip. What we see is that the attacker then tried to unzip their archive, right? File.zip, and they had a strong password of D. Oh, actually, no, not a password of D. They actually forgot their password. And so the very next command, we see them actually use PowerShell and grab it from another victim system, and just download this other DLL, right? So file new1.dll. So I thought that was kind of fun, is that they had a zip archive, had a poor password for it, actually forgot their poor password for it, and then just used PowerShell to download it from some other victim. So that was kind of fun. So fun tradecraft. Nothing, a lot of their commands weren't groundbreaking, but it was fun to see the way they interact with systems and how they were very successful. So in summary, so Mandiant basically did an investigation last year for an unknown attacker in a Fortune 500 financial environment. And then we were able to obtain a C2 server thanks to our client. And we did forensic analysis, and a lot of forensic value came from a Postgres database itself. So Postgres was really just a gold mine for solving this case and also looking for additional information. And then finally, based on this investigation, developed a tool called PostGrok to carve PostgreSQL rows from a image file. So just a couple of takeaways. One of the things I like is that Metasploit gets the job done. A lot of times I've heard, Metasploit isn't a tool that, real attackers use. Well, we actually see real attackers use Metasploit very frequently, and they're very successful with it. Just because you're not making your these custom malware or custom utilities or custom platforms, that you're not successful. Client environments are still getting pwned from Metasploit, and people who can really use Metasploit very well are very successful. Operational security. I thought it was kind of funny that really had the attacker just practice some operational security, this would have made this investigation or obtaining a C2 server kind of uninteresting. What if they had used full disk encryption and just encrypted their entire VM? That would have kind of hindered my investigation. What if they had deleted Postgres history, PostgreSQL command history, or used a different database name, or changed their password for the database to be something other than MSF? Just a number of different things that I think were kind of interesting from an operational security standpoint. They did delete a lot of stuff that they used on the Kali VM itself, but they just the Postgres database slipped their mind, and that turned out to be a huge forensic win. And then lastly, if you want a C2 server, just ask. Questions? Questions? Oh, geez. Yeah. Yeah, so the question was whether or not it affected the chain of custody when they sent us a C2 server, and the answer was no. So the chain of custody for us started at our client, because our client had the C2 server. So for us, it was client gives us C2 server, or actually not even necessarily gives us. We went to their site and imaged it. So we never actually took the C2 server, the physical rack mountable server itself. We just took an image on their site location. So chain of custody was really just starting at that location, took image to our forensic lab. Yeah, good question. Yeah. Good question. So that was a bit anticlimactic, I'll be honest. It turned out to not have any, it was really more opportunistic. I think if I had to take a guess, the attacker maybe knew that there was already a relationship between this third party and the client. So they probably leveraged that a little bit. But overall, no, they were not attacking them for any espionage gain or anything, or they weren't angry. They ended the contract, you know. Yeah. Anticlimactic, unfortunately. Good question. Any other questions? Cool. All right. Thank you, guys.